Hi there. Welcome to the loop compensation and simulation of a discontinuous flyback. Here on the screen you see the schematic of a very simplified flyback that I designed and simulated on a software called TopSpice. It's the software that I use. It comes with approximately 25,000 parts in its database, and it's the preferred simulator that I use. There's a bunch of other simulators. Another good one is LT Spice, although its library is kind of limited to whatever LT sells. Although you can install other vendors' parts, I prefer TopSpice. Anyway, I want to show you that the model that I'm using. Let's see right here. Okay, this model is a model that was produced by Christopher Basso, and it's a switching model for a current mode PWM. So that was just recently added to version 8 of TopSpice, and as a matter of fact, they added all of the Basso's switching models as well as Copex and the PWM, and they also added some other models from UC and TI. So like I said, TopSpice is it's a very capable simulator. Anyway, let me explain a little bit how I simulated this circuit. Let's see where my cursor is. Okay, this is supposed to be my transformer. Okay, and I'm using what is called the coupled inductor model. In other words, I define L1 and I have a little curly brackets, and I define LP as a primary inductance of the transformer, and I put LP, which is called a parameter, and I define it right here. That's called dot param. LP equals 120 microhenries. And then for the secondary, I use L2, and so I don't have to be calculating the secondary. We know that if you know the turns ratio of your a transformer, then your secondary LS is going to be R, the turns ratio squared, times the primary inductance. So in the curly brackets, I basically have NR times NR times LP. So all I have to do is define LP, which is right here, and then just define what my NR is, and automatically calculates what the secondary. I don't have to do any other calculation. Now the other thing that I want to point out is if these inductors, if you just put them in Spice, they're independent, but you have to add what is called the K or the coupling coefficient symbol. Basically tells a Spice that L1 and L2 are coupled, and then if you notice there's a 1 at the end, that means that that's the coupling coefficient. Now in this case, I set the coupling coefficient of 1, which means that it has 100% coupling. Now in real life, there is no such thing as a perfect inductor or coupling coefficient, or basically coupling coefficients will be anywhere from 0.99 to 0.92. So the higher the coupling, the higher or the closer you get to an ideal. And when you have a coupling coefficient that is not perfect, which is a 1, you end up with a leakage inductance which is in series with the primary. So you would have a little inductor right there. That means that this inductor, the leakage inductor, is not coupled to these two inductors, and basically you're gonna have a little parasitic. But for our simulation, I'm choosing to simulate an ideal, at least for this simulation, and later on I'll probably do another video showing how these parasitics do affect the operation of the power supply. Now, go ahead and erase this. Now, once you have your transformer, this part is my supposed to be the MOSFET. Now, for simulation purpose, especially since I'm running what is called a switching model, I use just a regular switch, and because it doesn't have any parasitics, meaning capacitance from drain to source, I added this capacitor here to simulate the capacitance from the drain to the source. So that's like I said, that's kind of like a parasitic. And then at the down here you have R8, which is the R-sense resistor. But basically that resistor is used to develop a voltage at this node, which is a representative of the current that is going through the inductor. So basically when the switch is on, you're going to have a little a ramp or a current ramp, and that slope of that is your Vn, whatever voltage. Actually this should be Vn, but in the schematic or in the simulator I have it as VDD, and the slope of that is defined as Vn divided by LP. So that would be the slope. And then as soon as you turn off the switch, it switches down or ramps down or pretty fast. Okay, going down this path, you have your diode, and then you have your output filter. And I did add this parasitic. No capacitors are ideal. There are always a little bit of resistance in the capacitor, and the capacitor that I would use in this case would be a stack cap, which is a bunch of multi-layer ceramics, and the value that I'm using is a 4.7 microfarad, and typically those have very low ESR, and the one that I use has about 15 milliohms of resistance. Now this power supply that I designed, or at least first pass demonstration, I picked specification of minimum input voltage of 24 volts, and I want to regulate at 12 with half an amp of current. So therefore I should have a load of 25 ohms, which is what this is. This is my R load. So I'll have half an amp flowing through it. Now that voltage is then fed back, and it is sampled here, is divided down, and we divide it down so we get 2.5 volts at this node, and then it goes into the PWM. Now inside the PWM there is a error amp, okay, and inside the error amp there's a little reference voltage. Typically it's about 2.5 volts, and this where it says feedback, that goes to the negative side, and then the output goes to this point. So this is a compensation network, and this is what I'm gonna compensate. These these are the three components that are used to compensate and set the dynamic response of the power supply. Now, being that this is a switch mode power supply, and it's a current mode actually, It samples both the voltage and the current. Now the current is, let me see, where's my cursor? Okay, here's my cursor. The current is sampled across this resistor, and it should look very similar to this. It looks, when it's off and it ramps up and then comes down. So if you put your scope at this node, you'll see a signal very similar to that, and that signal is fed back, and it's divided down a little bit, and then we have a little bit of filtering here. So this is a filtered current ramp. Okay, and the PWM uses it, and it has a second loop, but that loop does not set, or this composition does not set the gain or of the current loop. Okay, so in a nutshell, that's kind of what this power supply that I'm simulating consists of. And like I said, this is I'm using a switching model. Okay, now there's two types of models. Excuse me. There's two types of model. There's which the one that you just saw in the schematic, that's called a switching PWM model, and an example of that is the models that are used in the LT Spice program. They supply the models for their switching regulators, and basically it has the error amp and the digital circuit and the comparators and so forth. They're all use behavioral models inside in a black box, so to speak. And what these models are used for are to calculate all the voltages and the currents associated with the power supply. And in a sense, when you use the switching model, the results that you get in SPICE, they're very similar to what you would see in a oscilloscope. Basically, if you run the model, you can plot the current and voltages of the diodes, voltage and currents of the inductors, MOSFETs. Basically, you can analyze and check almost any voltage and current within that are modeled within your SPICE netlist. Okay. Now it does have disadvantages. The disadvantage is that since they're switching models, they have to go through a initialization, or in other words, since you're starting from the capacitors or filter output capacitors are 0, you're starting from 0, and it takes time for them to build up or come up to steady state. So it takes an extremely, in some cases, long time to do simulation. So that's one of the drawbacks. I mean, it's really good to get information as far as voltages and currents, but they do tend to run long. The more accuracy you want, the longer the simulation. Now, if you can cut down on the simulation, but then you lose the accuracy. Now, the other disadvantage is this one. You can't do AC analysis. In other words, you can't do a Bode plot of the loop and phase gain of the loop. You basically can't do this type of analysis in most of the SPICE simulators. Now, there is a simulator. It's not really a SPICE simulator, but it's called, I believe, Simplex. Now, they do use a added-on simulator. I forget what the name of it is, but it uses a non-Berkeley simulator, and basically you can do a schematic, a switch mode schematic, and it uses non-Berkeley spice to actually do a AC analysis. So of those people that are interested, you might want to do a Google and investigate how their simulator works. The other model that people use specifically to set the AC gain or the AC analysis or loop, they're called the average model. Now, the average model, if I've from what I researched, some of the first models were done by Chuk out of Caltech. Slobodan Chuk. In the 1980s, he created the space state averaging model, basically where you use very advanced math, which is takes a little bit of time, and if there's something that you want to change, let's say a component, then you have to redo all your matrices and so forth. So he was the first to model or make a model. The next step, big advance, was the PWM switch made by Vache Voporian, also from Caltech. I believe Vache studied under Chuk. As a matter of fact, Chuk was Vache's doctoral professor, and he created what is called a PWM switch, and he did that in the mid 1980s. What is neat about the PWM switch, it's kind of it's very similar to the small signal model that you use to model bipolar transistors or even the MOSFET. It's a model where you can 3-terminal device, and you can implement it in a SPICE. Although it's only 3, inside it has several SPICE lines to implement the PWM switch, and it works very well. And that's where his main was made, developing that model. Now there is another model, Ray Ridley. His model has a little bit of the PWM switch in it, but he developed it where he could predict the subharmonic phenomena of when you operate a power supply close to 50% duty cycle, you get subharmonic oscillations. Then the other models that are also available, the University of Colorado, I believe, COPEC, they have their models that they develop. That's Ericsson and Dragon. And the last model that I'm aware, I'm sure there's other models, there's the Ben Yakov, and that's the switch inductor model. I've used that one as well, and they all work pretty good. Now the only thing that sometimes these are a little bit more complicated. In other words, if you look at the net list, they have several line of codes, and they're well, depends. They're not that hard, but they're not as simple as one of the models that I'm going to introduce to you. And this model was introduced to me by my mentor, Jack Alexander. This is the best engineer that I've ever worked with. Jack Alexander recently passed away about 2 months ago, and this video is kind of in his memory to spread some of the stuff that he taught me to other engineers out there. Jack Alexander probably worked about close to 55 years in the industry. He worked in the Apollo program in Florida. After the Apollo program was winding down, I believe in 1969 he joined Data Corporation in San Antonio, Texas, and at Data Point he began designing power supplies or for the computers that Data Point was producing. By the way, Data Point, you might want to Google it. They inadvertently invented the first PC computer. So there's a very interesting story behind that. I think the two guys that founded Data Point was Gus, I believe Gus and Roach. Well, I forget what the names are, but anyway, these two founded Data Point, and employee number 2 was Jack Alexander. So, needless to say, they got one of the best engineers to join their group. After Data Point went belly up, or actually not belly up, but they were taken over, he left the company and he joined Southwest Research Institute, and that's where I met him and worked with. I met him in 2004 and worked with him until his retirement. He worked for the Space Science and Engineering Division, and while he was there, he designed over 125 space-rated power supplies that have flown in space or still flying in space. So the ones that are still flying in space is Cassini and New Horizon, and there's a bunch of other ones that have flown or still flying. Now, Jack model is the model that I use. The reason it's simple, but gotta remember it's a first order model, so it's something to give you a quick results. Okay, it is probably the simplest model out of all of these models that were developed by Chuk, Vache, Ray, and Kopek, and so forth. This is a very simple model. When you look at it, you say, wow, that's simple. Yes. Now, the other advantage is that it converges, meaning that you don't have problems that that the spy simulator crashes, and the simulations are very fast. Now, as always, when Jack developed this model or modeled his power supplies, he always did this. He always verified that the model was valid by actually building it and then taking a loop gain and phase measurement. And he used was what we call the Venable FRA, which is Frequency Response Analyzer. Once he had the Venable and the SPICE model, then he had full confidence that the model will predict everything. Okay, now here's a schematic of a actually this is simplified switching model. It's not a average model. Let me correct that. Okay, and it's basically kind of like the model that I have up there. And the point that I want to make is that typically all of this, let's see, inside all of that, that would be inside the PWM. Okay, so all of that would be part of the PWM. Now, what Jack did is he from this point, after the error amp, and let me change this color just so it shows it a little bit better. Right there. From this point to this point. Okay, so basically, if you take all of this, okay, what he did is he took that and basically he only left, let's see, where's the, okay, he only left the output filter and of course your error amp, okay. He left those alone, but this part, all of this, he substituted it with a simple voltage control current source. That's it. So basically he kept output filter, the error amp, and then like I mentioned, the output from there, he feeds it into a voltage control current source, and he's able to compensate the loop. He can design what his roll-off, his integrator, capacitor, and integrator resistor is. Now, one of the rules that he liked to use was he liked this voltage that controls the current source. He sets that at 1 volt. Okay, and then in the example, since this is a 12 volts at half an amp, okay, he knows that he needs an I average of half an amp to come out from the current source. So he sets the gain of this, I guess since it's current over voltage, the transconductance, he sets the gain of that as the I average divided by 1 volt. So in my case, since I want half an amp, I divide by 1, so I would set the gain to 0.5 amps per volt. Now in the simulator, I don't put the amps per volts, I just set it to 0.5. Okay, so this is, I mean, as simple of a model that you can get. Like I said, it converges, and it's a first order. I mean, it doesn't predict subharmonics, but it's good enough that you can, it'll get you probably about 90% or more close. And like I said, once you have this model, you always verify that the model is correct by actually running a plot of the system loop. Okay, now another thing that he taught me was how to compensate. Okay, now since it's a current mode, okay, and remember he models the PWM, the MOSFET, and the transformer and so forth. He models all of that stuff with a voltage control current source. Okay, so since you have a current coming through here, and if you were to do a Bode plot of this, you would see that you would get a response like this. Okay, now at this point, since this breaks down, that's a pole, and then this point actually breaks up, so that's actually a 0. Okay, so what produces what? Well, in this case, this pole is produced by this combination. It's produced by your load and your output filter capacitor. So basically that pole is 1 divided by 2 pi CO times RL. Okay, so that is that. Okay, then this 0, forgot to put the Z. Okay, that 0 is produced by the combination of the output filter and its own ESR. Okay, so that would be 2 pi ESR times CO. Okay, so you end up with this type of a plot, and of course it's over frequency. And then in regards to the error amp, since it's a card mode, we use a type 2 error amp. Yeah, type 2. And if you were to plot, let's say you have your integrator mislabeled here. Let me fix that. Okay, sorry. Okay, that's a cap, and that should be CINT, and this is my RINT. Okay, so if you were to plot that, you would see a waveform very similar to this. At, let's say, a frequency of 1 Hertz, well, typically, let's say if the capacitor was shorted and didn't have that cap, the gain of this would be the integrator divided by RA, and you would have an inversion. Okay, now at low frequency, the X of L, the reactance of the capacitor, is very high, while this will be lower. And as far as impedance, the capacitor dominates. So you have a high impedance divided by RA, which typically will be lower, so you end up with a high gain. Okay, and then as you increase the frequency, the gain decreases as your X of C goes down. And then at this point, which is F0, which is where the integrator resistor and your integrator capacitor are equal, then that forms a 0, and that's basically calculated by 2 pi R integrator times C integrator. Okay, so at this midpoint, okay, then the gain is really R, the integrator, divided by RA. And typically this RA will actually be a R Thevenin of the sample resistor. Basically, you'll have a that resistor goes to V out. Well, this is that, and it's the R Thevenin combination of these two resistors. Okay, so then as you increase the frequency, then you come to this point. Okay, and that is a pole, and that pole is established by the high frequency roll-off capacitor, and what it does is shunting this two impedances. It becomes dominant. So then the X of C of the roll-off becomes much smaller in comparison to RA, and you start having a decrease of gain. And the pole is calculated 2 pi R integrator times C of the roll-off capacitor. So now having and seeing these two, you have the output filter, you have the error amp. Jack's method or basic idea was to set the 0 of the error amp equal to the pole of the output filter, and set the pole of the error amp should have put error amp equal to the 0 of the output filter. So basically, what does that mean? Okay, well, if you line it up, basically you want this F pole, well, you want to cancel, you want to place the 0 at the same frequency that your pole of the output filter. You match these two, and basically you're going to cancel. Okay, and then the other is this F0. You want to set the pole of the error amp, you want to set it at the same frequency as this 0. And basically you want cancellation of both. They're going to cancel each other. Now, since you line these up, then the total gain is actually the summation of both these two plots. So let me change the color. I'm going to use green. Okay. So if you were to, like, I can draw straight. So basically, if you were to take the summation of these two plots, you should get something that looks like this. Okay. Basically, there's 0 dB per decade here, but you do have a negative 20 dB here, so the result is negative 20 dB here. Okay, here you have a negative 20 dB, you have 0 dB here. Okay, the result, you get negative 20 dB here. Here, 0 dB, you get, here you have negative 20 dB per decade. Result, you got negative 20 dB. Okay, so basically that's Jack's way of compensating, and this is the method that he used to set all of those power supplies traveling in space and around Earth. So let me see if I can do a quick simulation. This is the switching model, the AC model. Let's see if I have the AC model. Here's the AC model. Again, I have my output filter, ESR, my load. Okay, and then I feed back that voltage, and I'm going through my sampling resistors. So this point is my feedback. So there's a Thevenin equivalent of these. It's close to 4 point something K. I have an integrator resistor, integrator cap, high frequency roll off, and then this. Now I did put a little bit of attenuation, but it's hardly anything. It's 2K and 100K. So basically you get the full voltage here. So that voltage is fed back or fed to your current control voltage source. Okay, and then at the non-inverting side you put your reference voltage. So, and since the current is flowing downward, in reality I want it to flow up, so I had to set the gain to negative 0.5. Now I'm gonna go ahead. One way of measuring the loop response of a power supply is typically you insert a resistor. We call it a venable resistor, and typically it can be anywhere from 10 ohms to 100. And then we connect a venable instrument, which is the frequency phase array, frequency response analyzer, and it injects a signal, and it measures the sine wave that it injects, and then by the time it comes back as a sine wave, but it's delayed and it has different amplitude, and it calculates what the gain phase by measuring those two signals. Well, we can do the same thing on SPICE. We label this node as in, and we label this out, and it's convenient because it is the output, and we put a voltage source, and we actually enable the AC. Okay, and then I defined it, which is what this line says. It says in the top SPICE we have a command says pound calc, and then I set a variable. In this case I said loop is equal to the loop, or actually let me change this. Let me change it to gain, because it's the gain. Gain. Probably be a little bit more appropriate. Be gain, and then I'm gonna plot the dB of the gain and the angle of gain. Okay, so once I have these two, I'll move these up here, these two SPICE commands. Okay, and define what the gain is supposed to be, which is really V out divided by Vn. That will give me the gain of the loop. And I go to AC sweep. I selected 100 points per decade, starting frequency of 1, and a stop frequency of 10 megahertz. Okay, so I run it. Okay, so that's my loop response. So, and these are just numbers, or the values of these are just picked. It can be any values, but those are the values that I got for right now, at least for this example. Okay, so the frequency response, or the bandwidth, we also call it a crossover, is where it crosses, or where the gain crosses 0 dB. In this case, it crosses at 2.34 kilohertz. And once you have that, you measure the phase, and the phase in this case is 31 degrees, which is not acceptable. Typically you want 60 or more. Jack used to set it to anywhere from 60 to 90 was acceptable. So in this case, this would not be a very good supply. It would be ringy. Okay, so let's try Jack's method. Okay, so basically what I like to do is I like to match, I want basically unity gain at the midpoint. So I try to make these two resistors. In other words, I try to make the integrator resistor approximately equal to the Thevenin equivalent of the 19K and the 5K. So without getting a calculator, I'll just set it to 5K for right now. Okay, so that's the starting point. I set this to 5K. Now I want to set this integrator cap. Okay, now to set the integrator cap, remember this will produce a 0, so we want to set this time constant of these two equal to the time constant of the capacitor and the load. In this case, my load, since I'm using 2, it's supposed to be 50 ohms. I have a load here and I'm using another 50 ohm here, so in reality I have 250 ohms in parallel is 25. So what I can do is I can multiply, let's see, 25 times the capacitor, the capacitance of the output filter, which is 4.7 microfarads. Okay, so I get 117 micro, and then I'll divide that by 5K. Okay, 5K. So I end up with 23 nanofarads. Okay, so I have that. So now I run it, and you notice it had a little curve. This kind of straightened out. Okay, so if you notice, there's this other let me see, there's a pole here, and then a high frequency 0. Okay, so now I want to set my roll-off. Now this roll-off in combination with this integrator resistor will give you your pole, and you want to offset or cancel the 0 that's produced by the output capacitance in the ESR. So again, I multiply 4.7 microfarad divided by 0.015 ohms. Okay, I get 313 micro divided by 5K, and I get, let's see, did I do that right? Let me try to do that again. 4.7 micro times 0.015 divided by 5K, 14. Okay, I get approximately 14 picofarad. Okay, I run it. Wow, that's a beautiful Bode plot. Basically, I have a Bode plot. It's got approximately 90 degrees, and I have a frequency of approximately, let me see, 4.2 kilohertz. Phase margin is 89. Okay, well, maybe this bandwidth is too low for you. Okay, so what do you do to increase it? Well, what you can do is we can increase it, let's see, it's 4.2. Let's say we want to increase it by a decade, in other words to 40. See if we can do that. Okay, and if we increase this to 50, I should decrease this by a decade as well. I should decrease this by a decade, but it's probably not doable. Okay, so now I was able to bring the frequency up from 4K up to 43K. Okay, so basically by adjusting this resistor first, up or down. You can increase the gain by increasing the resistor or decrease the gain, and once you set your value, then you have to calculate these two, your roll-off and your integrator capacitor. So that's how Jack's simplified way of setting control loops works, and it works very well. In the second video, I'll compare, or I'll verify Jack's AC model against a transient model to see whether they agree or not. Hope to see you. Bye.